Hello Doctor, in this video we are going to talk about what we have done for the group assignment for stochastic modeling in physical oceanography MTS5054. In our group there are 7 members which are Ahmad Faizi, Nadia Maisara, Nur Fakira, Nurul Latifa, Siti Amira, Wan Sulaiman and me Tay. In session 1.0 introduction, we are going to talk about what we have done in this paper draftly. To construct a stochastic modeling in oceanography, one of the important things is the amplitude of the wave. The amplitude of a wave is crucial in determining the wave energy and impact. The amplitude is defined as the maximum displacement of a particle from its equilibrium position in the median through which the wave is propagating. Wave amplitude corresponds to the vertical distance between the crest and trough of a water wave and is typically denoted by A. The most frequent probability distribution of a wave amplitude is based on the assumption that the wave spectrum is narrowband. Under this circumstance, the wave profile slowly changes with a constant period, with the existence of a single peak or trough occurring every half circle. However, in the real world, it often happens that a wind generates waves that do not follow narrowband characteristics. In this case, we refer to such wave as non-narrowband wave. In this study, we will introduce the probability density function for amplitude or wave height or period for narrowband wave and non-narrowband wave. Hence, the study serves as a comprehensive resource for understanding the stochastic property and probability distribution applicable to wave amplitude and height, offering valuable insight into the statistical characteristic of random wave and comparing both narrowband and non-narrowband wave spectra. Overall, the study aims to describe the probability distribution and stochastic feature related to wave height and amplitude under different scenarios. The fundamental presumptions of the study are that random waves are normal Gaussian random process, weakly steady state, and ergodic. Meanwhile, wave height, period, and direction of travel must all be taken into account for a thorough understanding of wind-generated random wave. If there is any association at all, the combined inference of height, period, and direction needs to be carefully taken into account.
2.0 Amplitude distribution with narrow band spectrum. 2.1 Probability density function. Basically, in this subtopic, it explains the derivation of the probability density function, which is known as the narrow band random process. From the derivation, the probability density function is said to be the Rayleigh probability distribution. From the probability density function, it also can be derived into the half-cycle excursion and probability distribution of amplitude with a narrow band spectrum. Firstly, the derivation of probability density function. The random process of xt is assumed to be normal random process with the condition of zero mean and variance. From the equation, we can form the equation of xc and xs, where both are said to be statistically independent normal random variable, which lead to zero mean and variance, where it is also equal to area under the spectral density function of xt. From that, we can also form joint probability density function of xc and xs. Substituting amplitude into xc and epsilon into xs, we get the joint probability density function of amplitude and epsilon. Integrating the function with respect to epsilon, we will get the marginal density function, or also known as Rayleigh probability distribution. And if we integrate the function with respect to amplitude, we will get into the half-cycle excursion. And from the half-cycle excursion, if we differentiate it, the equation with respect to zeta, we will get the probability distribution of amplitude with a narrow band spectrum.
The wave envelope process is a mathematical representation of wave profiles that employs symmetric curves passing through wave crest and throw. Rather than directly dealing with amplitude, this process uses upper and lower envelopes to connect peaks and throw. The wave profile is expressed mathematically as equation 2.2.1, where an is a normal random variable with zero mean and a specific variance. The mean frequency, denoted as omega bar, is defined as the ratio of the first moment m1 to the zeroth moment m0 of the wave spectrum. For non-narrow spectra, the complex envelope function can be determined. The wave profile is then written in terms of the envelope process rho t and total phase chi t, represented as xt equals to xct plus ixst. The Hilbert transform, denoted as x tilde t, is introduced to evaluate the envelope process rho t. The Hilbert transform of a real-valued function xt can be seen at equation 2.2.4. The envelope of the complex process zt, composed of the original wave record xt and its Hilbert transform x tilde t, is given by equation 2.2.5. In practice, envelopes are often obtained from filtered records. It is crucial to consider the effects of lower and upper frequency cutoffs during filtering to ensure accurate representations of wave profiles.
Section 2.3 is about the distribution of two-wave amplitude. Let us consider the dry probability distribution of 2 points of an error process, st and st plus tau, that can be presented in the form rho t exponential ivt separated by the time tau. From the equation 2.2.2, we can have the equation 2.3.1, where it's about the sct and sst in the form of n, omega bar, t, and epsilon n. Since they are normally distributed with zero mean, the random variable sc1, ss1, sc2, ss2 are the dry normal distributed with the following two properties, 2.3.2 until 2.3.5, where the exponential of each variable is equals to 0. The covariance of the sc1, ss1, sc2, ss2 is equals to 0. The variance for each variable are equals to sigma square. The covariance of the sc1, sc2, and ss1, ss2 is equals to the rho. For the covariance of sc1, ss2 is equals to the covariance of negative covariance of the ss1, sc2 equals to lambda. From the properties above 2.3.2 until 2.3.5, we can have the covariance matrix of sc1, ss1, sc2, ss2 as the following equation, 2.3.6. Since they are normally distributed, we can have the dry normal probability density function with S transpose equals to sc1, ss1, sc2, ss2 as the following, 2.3.7. We now transform the random variable to amplitude and phase, a1, epsilon 1, a2, epsilon 2 using the function relation 2.3.8, 2.3.9. And we can have the dry probability density function a1, epsilon 1, a2, epsilon 2 becomes 2.3/10. Since we only want the amplitude dry probability density function, so we integrate the dry probability density function of f a1, epsilon 1, a2, epsilon 2 with respect to epsilon 1 and epsilon 2 to conduct the dry probability density function of amplitude a1 and a2, 2.3.11. Lastly, assume epsilon 1 minus epsilon 2 be a single variable, and we can have the dry density distribution of amplitude a1, a2 as the following equation, 2.3/12.
probability distribution of peak to trough excursion wave height is one of wind generated wave condition in the narrowband spectrum by assuming the magnitude of the excursion is twice the amplitude. This concept looks similar to the probability density function of wave with a non-narrowband spectrum, but may not be acceptable to say it is the same because twice the magnitude of positive maxima does not imply the wave height. Another assumption that is said better of probability distribution of wave height is to consider either the sum of two statistically independent amplitudes or, to be more precisely, the sum of two amplitudes separated by one half of the average period. In this part, the Rayleigh distribution is the common distribution used to describe the amplitude of random wave height in deep water. So the Rayleigh distribution is given by equation 2.4.1. The probability distribution function of the sum of this variable h can be obtained by considering the two Rayleigh probability distribution with independent amplitudes for the derivation of wave height distribution, as shown in the equation 2.4.2. By writing the wave height as h equal to a1 plus a2, the probability distribution function of wave height can be expressed as below. In the equation 2.4.3, Typhoon assuming that the period is constant and is the mean period given by t equal to 2 pi over omega pi, where omega pi is the mean frequency. The probability distribution function of wave height is as in the equation 2.4.4. After the evaluation, the probability distribution of wave amplitude can be transformed into equation 2.4.6. And the probability distribution function for the peak to trough excursion wave height can be derived as shown in the equation 2.4.7, where sigma square is the variance of the xt and rt over 2 over sigma square. If the bandwidth of a spectrum is 0, rt over 2 becomes negative 1. So the function h is equal to equation in 2.4.1.
My name is Norfakira Afrina binti Azizi. For this study, I will explain about significant wave height. Significant wave height is denoted by Hs. The severity of sea condition is most commonly presented by significant wave height, which is also defined as the average of the highest wanted observed or measured wave heights. The significant wave height can be evaluated using the Rayleigh probability density function. Meanwhile, for a narrow bandwidth spectrum, wave height follows the Rayleigh probability distribution. As you can see here, given Rayleigh distribution as fx is equal to 2x over r exponent negative x squared over r for x more than and equal to 0 and less than infinity. In this distribution, parameter r is equal to 8m0, where m0 is the area under the spectral density function. From this Rayleigh distribution, significant wave height can be obtained as Hs is equal to square root ln 3 plus 3 square root pi of 1 minus phi square root 2 ln 3, then multiply by square root r. Then we get Hs equal to 1.42 square root r. For significant wave height, parameter r is equal to 8m0. So at the end, we will get Hs is equal to 4.01 square root m0. We can say that the significant wave height is equal to 4 times the square root of the area under the spectral density function with narrow band random process assumption. We make a comparison between significant wave height and peak to trough excursion, where both are different in terms of parameter r. For peak to trough excursion, r is equal to 8 times variance, while in significant wave height, r is equal to 8 times area under the spectral density function. Both significant wave height and peak to trough excursion use Rayleigh distribution.
The joint probability density function for wave height and period was initially developed by Langmuir, Huygens in 1975, with a revised version introduced in 1983. This distribution provides a mathematical framework for understanding the simultaneous occurrence of different wave characteristics. Assuming waves to be a Gaussian random process, the wave profile is expressed as equation 2.6.1, where an is a Gaussian random variable. The relationship between amplitude and phase is given by equation 2.6.2, highlighting the connection between the amplitude and phase components of the wave profile. Using spectral width parameters and relationships, the marginal probability density function of the phase velocity is presented as equation 2.6.3, indicating the probability distribution of phase velocity. To facilitate dimensionless presentation, the dimensionless amplitude C equals to rho over square root m naught and dimensionless period eta equals to capital T over capital T bar are introduced, where m naught is the area under the spectral density function and capital T bar is the mean period. Following Longuet-Higgins derivation, the joint probability density function of wave height and period in dimensionless form is given by equation 2.6.4, providing insights into the joint distribution of wave characteristics. By employing the mean frequency, which is the omega bar, a significant advantage is gained in developing the joint distribution of wave profile as t and its velocity as dot t. In the context of wave analysis, the joint probability distribution of wave height and period is related to narrow-banded wave spectra. In narrow-banded spectra, energy is concentrated around a central frequency or period, and this concentration is reflected in the joint probability distribution. Specific C states characterized by narrow-banded spectra may exhibit a higher likelihood of certain combinations of wave height and period associated with the dominant frequency.
Section 2.7 is about the probability distribution of wave period. First, let us consider the expected number of wave crossing of the level s with the velocity s dot per unit time. The time travel a distance ds with velocity s dot is equals to ds over s dot. The joint probability density function can be written as f as s dot ds ds dot. The number of crossing per unit of time with velocity s dot can be calculated by using the time probability density function divided by the time travel a distance ds with velocity s dot. So we can have the equation 2.7.1. The number of crossing of the level s irrespective of the velocity magnitude can obtain as the equation 2.7.2. And if we consider only the up crossing s equals to 0, we can have the equation 2.7.3. Just like how to calculate the period, the frequency equals to 1 over t. To calculate the period, we can have t equals to 1 over f. So we can have the equation, the average zero crossing period, t0 bar, is the inverse of n0 bar, where is equals to 2.7.4. By integrating the joint probability density function of wave height and period 2.6.4 with respect to sigma, we can derive the probability density function of the wave period as 2.7.5, where n equals to t over t bar equals to mean period equals to 2 pi square root m naught over m1, v equals to spectral wave parameter equals to square root u2 over u naught 1 over omega bar. The mean of the equation above 2.7.5 is infinite and the variance of the distribution does not exceed theoretically. Therefore, Rogers Higgins suggests that use the average zero closing period T0 bar, we can have the dimensionless average period 2.7.6.
2.8. Joint probability distribution of wave height and direction of wave energy travel. To estimate the probabilistic relationship between wave height and direction, it considers the joint probability distribution of the envelope process of wave displacement and two rectangular components of the horizontal water particle velocities. By taking into consideration of wave in a finite water depth H and let that eta t, ut and vt be wave displacement and the two rectangular element of the horizontal particle velocity. Basically, we have the equation of eta t, ut and vt. Following the derivation in subtopic 2.1, based on equation 2.13, we get eta t equal to eta c cos omega bar t plus eta s sin omega bar t, and also the same goes to ut and vt. There are 6 random variables involved in this study which are normally distributed with zero mean. The random variable with subscript C and subscript S are statistically independent. Let the NP as the dimensionless wave amplitude and sigma as the phase of the surface displacement. Then we will get the equation of NC, NS, UC, US, VC and VS.
Then, the joint normal probability density function of 6 random variables is transformed to the joint probability density function FNPUPVP as shown in the equation 2.8.9. The direction of wave energy travel is given by alpha inverse tan Vp over Up. Hence, in order to obtain the joint probability density function of wave amplitude Np and direction alpha, the random variables Up and Vp are expressed in the terms of the polar coordinate W alpha. By applying the functional relationship, the joint probability density function FNPUPVP in the equation 2.8.9 is transformed to the joint probability density function FNPW alpha. Then, by integrating this density function with respect to W from 0 to infinity, the desired joint density function of wave amplitude in dimensionless form NP and direction of energy traveling alpha can be derived as in equation 2.8.10. In particular, for the case of directional distribution of wave energy that is said to be narrow and symmetry, we can simplify the equation as shown in the equation 2.8.11.
3.0 Wave maxima distribution with non-narrowband spectrum.
Assalamualaikum and hi. I am Ahmad Faizi and now I will explain about the probability distribution of wave maxima with non-narrowband spectrum. The profile of wave that observed in severe seas is much more irregular compared to what has shown under narrowband process. The wave profile is irregular as it frequently contains two or more peak or trough within each half cycle. So, the wave amplitude cannot be clearly defined. In this situation, we will define the local maxima and minima of the wave profile and will develop the probability density function. First of all, we define the local maxima and minima of both positive that is above mean value and negative that is below mean value of a random process. So the figure 3.1 show the definition of local maxima and minima of non-narrowband random wave. Suppose that xt is wave displacement. x dot t is the wave velocity and x double dot t is the wave acceleration. So this will be used later for developing the equation. The local peak and trough are located on the positive side that satisfy the condition of xt is bigger than 0 and x dot t equal to 0. So they are defined as positive maxima for x double dot t less than 0 and positive minima for x double dot t is bigger than 0. Similar to for the peak and trough on the negative side that defined as negative maxima for x double dot t less than 0 and negative maxima for x double dot t bigger than 0. So the main focus is to derive two different formulations that are available for distribution of local maxima and minima. The first one is the probability distribution of positive maxima only or negative minima only. And the second one is the probability distribution of maxima or minima including positive and negative minima. To develop the density function of positive maxima, which denoted by z, we need to consider the probability that z will exceed a certain level of zeta. So capital F zeta is the cumulative distribution function of z, and E is stand for expected value. The expected number of positive maxima above the level zeta per unit time is written as in equation 3.0.1. And then, by letting zeta equal to 0, we may write the expected number of positive maxima per unit time as in equation 3.02. The range is now changed from 0 to infinity. And then, we can define the probability density function of the positive maxima f zeta as shown as in equation 3.0.3. For a Gaussian random process with zero mean, x dot and x double dot are statistically independent. In order to evaluate the denominator in equation 3.0.3, first we need to integrate with respect to x and then integrate with respect to x double dot. Equation 3.04 show the final equation for the probability density function for the positive maxima. And now, we want to develop the second probability distribution of maxima that including both positive and negative maxima. The procedure is the same from before, except the sample space now is extended into negative range, which is from negative infinity to infinity. The second probability density function is shown in equation 3.0.5 with the range of negative infinity to infinity. Noted that the parameter epsilon is called bandwidth parameter of spectrum. Epsilon equal to 0 represent a random process with narrowband spectrum. The bandwidth parameter here play a significant role. The value of parameter epsilon is influenced by the magnitude of the fourth movement in the wave spectrum. The extent of this influence is largely determined by the frequency range where the dominant wave exists. That's all for section 3.0. Thank you.
Now we are going to this subchapter 3.2, which is half cycle execution. In the world of wave, a half cycle represents the journey from the highest point, which is peak, and to the lowest point, which is trough, and back to the peak. Now we want to analyze this wave statistically, specifically looking at their amplitude, how high or low they go during the half cycle. Basically, this half cycle execution have two types. The first one is type 1 execution, which is determined as one that cross the zero line, moving from positive to negative or vice versa. And the second one is type 2 execution. This one is stay on one side only, either consistently above or below the zero line. Okay, before we proceed, as we look at the figure, in this case occur type 1 execution A1 to C and type 2 execution A2 to B. Type 2 must be delayed by taking into consideration to the frequency of occurrence of each execution. This is for understanding by separating the statistical properties of type 1 and type 2 half cycle execution to accurately understand the behavior of wave amplitude during each type of execution. By delayed, the maxima belonging to type 2 execution arise when evaluating the probability distribution of type 1 execution and ensuring that the statistical analysis accurately reflect the properties specific to the type 1 execution. Now we jump to probability of occurrence of type 1 and type 2. These are probability of occurrence that we look how often these different types of execution happen. The first one is P1 is the probability of type 1 execution on the positive side, and P2 is the probability of type 2 execution on the positive side. Okay, along the way, this equation is for getting a probability density function. Okay, the first one is for the type 1 execution. We are interested in the statistical distribution of this type 1 execution, specifically when they are descending. Imagine the probability of a wave coming down after reaching its peak. The second one is type 2 execution. Now for type 2 execution, we are considering the difference between the highest point and the lowest point. This helps us to understand the range of the wave behavior on the positive side, which I explained before this. By bringing all the together of type 1 execution and type 2 execution, we are creating mathematical expression, probability density functions, to understand how likely and how intense these different type of wave behavior are, which is the equation of 3.1.11. And then we can have the Q1 and Q2, which is the weighting factor for each individual for type 1 and type 2. And then from that equation, we can simplify and we get half cycle execution as 3.1.12. In simple term, Q1 reflect the weight of type 1 execution in the grand scheme, balancing their influence against type 2. And Q2 does the same for type 2 execution, ensuring a harmonious portrayal of their statistical significance. Overall, through this equation, we can gain a mathematical framework to interpret and predict the probabilities and intensity of various wave behavior. For conclude, this equation serves as a powerful tool for uncovering hidden pattern in a wave statistic, offering insight into the complexity of a half-cycle executions and guiding further exploration in the wave analysis.
Next, we will talk about joint probability distribution of positive maxima and time interval. The strict definition of amplitude and period cannot be defined when dealing with multiple crests or what can be referred as positive maxima. The initial step involved by acquiring the joint probability distribution of the maxima and their corresponding acceleration. This distribution needs to be transformed into joint probability distribution of this maxima and period. The joint probability density for positive maxima is denoted as this symbol, and time interval t that is crucial for understanding the statistical behavior of the ocean wave. The probability of positive maxima surpassing a specified level zeta along acceleration x double dot exceeding is determined by this equation. And then the equation in 3.2.1 is represent the joint probability density function of positive maxima and acceleration. So this equation summarizes the joint probability density function of wave displacement, velocity, and acceleration, providing a holistic insight into the characteristic of wave.
For equation 3.22, the dimensionless joint density facilitating comparison across different waves is derived as 3.22. In this equation, that are represented with the dimensionless joint density of positive maxima and its time interval, and also is have the joint distribution of maxima and acceleration with the denote the significance of wave height. This equation is significant because it allows us to transform the joint distribution of maxima and acceleration to dimensionless form, enabling comparison across different waves. By normalizing the joint distribution with the significant wave height, we can obtain the dimensionless representation that facilitate meaningful comparison. And then we continue to equation 3.23, the dimensionless joint probability density function of wave height and period is presented as 3.23. It's similar like 3.22. It had represent the dimensionless joint probability density function of wave height and period, joint distribution of wave height and period, and denote the significance of wave height. Okay, for this equation is significant because it enables the assessment of wave characteristic independent of a specific wave scale by normalizing the joint distribution with the square of significant wave height. We can obtain a dimensionless representation that allows for the analysis and comparison of wave property without being constrained by specific.
Conclusion. Narrowband and non-narrowband wave spectra are covered in this study. A single peak or trough occurs during each half cycle of a narrowband wave's slowly varying wave profile. The assumption of a narrowband spectrum is often valid for wave produced by modest wind speed. When this circumstance is met, wave amplitude obey the Rayleigh probability rule, the most widely utilized probability distribution for a wave amplitude in marine system design. On the other hand, non-narrowband wave have a quickly fluctuating wave profile that has several peak and trough throughout each half cycle. Wave infinite depth of water are typically regarded as non-Gaussian random process and are viewed as non-linear. The assumption of a non-narrowband spectrum is typically relevant to wave produced by strong wind or in shallow water. Wave amplitude in this scenario is distributed according to a different probability distribution. A non-narrowband spectrum encompasses a broader range of frequency, signifying a more diverse composition of wave component. The study of non-narrowband wave spectra is essential in understanding the behavior of ocean wave. Researchers often analyze non-narrowband wave spectra to gain insight into the overall energy distribution, the occurrence of dominant wave component, and the statistical properties of the wave. Hence, to fully understand wind-generated random wave, consider wave height, period, and direction. The combined effect of height, period, and direction is crucial. With data in the ocean show that period dispersion and height dispersion are not statistically independent.